Hi, in this video I'm going to show some first order systems, and the first one we're going to do, which I think is the simplest, is a simple water tank. Okay, so here you have a water tank. It's got some water in it, and it also has a pipe coming in where water's flowing into the tank, and there's a pipe right at the bottom where water leaves the tank. Okay, and the rate at which the water enters the tank is going to be given by Q1, and we'll say a bit more about that in the next slide. And the rate at which water leaves the tank is given by Q2. One other thing is that the height of water in the tank, so as the tank fills up, right, the height of water changes. That's going to be given by this variable called H1. Right, so the height could be in centimeters or feet or meters or whatever you want. Okay, so what we're going to do is we're going to describe this tank using a differential equation, and the way we're going to do that is we're going to define the volume of water in the tank, V, and we're going to assign the units to K1 and K2 as the volume of water per unit time. So there might be, and I've got an example here, liters per second. So the water might be flowing in to the top of the tank at 5 liters per second, and it may be leaving the tank at 3 liters a second. All right, and that's convenient because now I can describe the rate of change of the volume as the difference between the amount of water coming in and the amount of water leaving. And since these two here are in volume per unit time, this side here will also be in volume per unit time. So this dV by dt describes the rate at which the volume is changing as a result of water coming in and water leaving. All right. So this is the equation we'll start with. Now the next thing I want to do is the following. I don't really want to measure how fast the volume changes. What I'm really interested in is how fast the height changes. Okay, H1. I'd really like to know how fast that changes, because you can imagine, let's say the tank is empty. Let's say at time 0 the tank is empty. That means the height of water in the tank is 0. And at some later time, maybe 2 minutes later, the height is now 2 centimeters. The height of water is 2 centimeters, and maybe after 30 seconds, maybe the height of water is now 20 centimeters. Okay, so the tank would start to fill up. And what I'd really like to describe is how the height of water changes over time. So the volume here, the rate of change of volume, is not really what I want. So somehow I've got to change volume to height. Well, the way to do that is to make one other assumption, and that is the water tank is cylindrical. Right, so it's a round tank in the shape of a cylinder, and that means it has a cross-sectional area which I'll call A. Right, now if that's the case, then the volume of water in the tank is just the area, cross-sectional area, times the height of water. And remember again, the height, H1 is the height of water. So what can I do with that? Well, what I can do with that is I can differentiate that equation. Right? So that equation is the volume equals the area times the height. And I can differentiate with respect to time, and all that happens is if I differentiate V, it turns into dV by dt. If I differentiate H1, it just turns into dH1 by dt. What happens to the A? Well, the A is a constant. I mean, the shape of the tank is not going to change. All right, so A is effectively a constant. All right, so that's why that's left there. Okay, so now we've got this equation. We're going to use this as follows. So first of all, that's the first equation I've got. I didn't like that. Let me get rid of that. That's the first equation. Okay, this one here. And the second equation we just had was this one. Okay, and notice what I can do now is I can take this portion here and substitute it for that, because these two of course are equal. And if I do that, I end up with this. Okay. Now normally we wouldn't have the area on the left hand side, and I'd probably cancel that and then divide both sides by A, and that would give me the rate of change. So let me write that down. Rate of change of water is the rate of water coming in minus the rate of water leaving, all divided by the cross-sectional area. So this is the form I want it in now. Okay. Alright, so what do we now do next? Well, the next thing is we have to decide what is Q1 and what is Q2. Now Q1, this one here, is the rate at which water is coming in, and essentially we determine that. We can decide how fast the water is coming in. In fact, we can just make it a constant, and so I'm going to make it a constant, right? So it's just a number, and maybe it's 5 liters per second. Alright, so Q1 is a constant, so that stays as it is. The more interesting one is Q2. Now you could imagine that if the water level were low in the tank, that would mean there wouldn't be much water pressure, and presumably Q2 is here would also be low. But imagine now that the tank fills. Oops, let's get the tank filling. The tank fills, the water pressure goes up, and presumably much more water flows out as a result. Alright, so there must be some relationship between the height of water and the rate at which the water flows out. Well, luckily the physicists have actually sorted that out. In fact, there was a scientist called Torricelli who discovered what the relationship was, and it's now called Torricelli's law. And all that says is that the rate of flow of water out of a tank is proportional to the square root of the height of water in the tank. It's an odd looking relationship, not perhaps one you'd expect, but that's basically the law that governs how water leaves the tank. Now we're not going to use that though. We're going to keep things simple. Okay, we're going to keep things simple, and I'm just going to assume that the flow of water out of the tank is directly proportional to the height of water, right? So we keep it simple. So instead, I will assume that Q2 is directly proportional to the height of water. Now that's not a bad approximation. In fact, when the tank is fairly low, that probably works out quite well. But we'll keep things simple by just making that relationship. And if it's proportional, of course, that means it must equal some constant times H1. And in fact, that's what I've got here. Okay, so that's our relationship for Q2. So with that in hand, we have the final equation, which is this here. So the rate of change of the height of water is Q1 minus K times H1 divided by A. Now maybe I should say something about K. K is some kind of constant, and that constant will be some function of how wide this pipe is here. Alright, so if the pipe is really narrow, then the K was probably going to be small, but if the pipe is really wide, then the K is probably going to be quite big, but we won't worry about that now. The other thing, of course, is I've moved the area over to the right hand side, so it's underneath the terms. Okay, so there it is. So just to show it again, that's the equation that we've got. The big question is why is that first order? Okay, so it's first order because the left hand side, this piece here, is only the first derivative. Okay, it's only the first derivative. So it's not a second derivative or third derivative, it's a first derivative. So there are no higher derivatives. Okay. The other important point to bear in mind is it's only a single differential equation, meaning there is only a single variable in our system. Alright, so that pretty much, maybe I could summarize that. So to be first order, number one, the derivatives, or the derivative, should also be first order. Right, so it can't be a second derivative or third derivative. The second thing is there should only be a single variable. Be a single variable. And the single variable in this case, of course, is the height. All right. So if you had two variables, let's say you had two tanks, one after the other, and you had two heights, that wouldn't be first order. Okay, and that's it.